Have you ever seen a tiny black plastic rectangle with little metal legs sticking out of it? It might not look like much, but it could be one of the most important inventions in electronics history, the Operational Amplifier, or Op-Amp for short. Today, we're going on an adventure inside a true classic, the MA741. Released by Fairchild Semiconductor way back in 1968, this little chip was a game changer. It packed a powerful and versatile circuit into a single, affordable package, making complex electronic designs accessible to everyone, from professional engineers to hobbyists tinkering in their garages. It's like the Swiss Army knife of analog electronics. Before we dive into its silicon heart, let's get to know its external shell. The 741 most famously comes in an 8-pin dual inline package, or DIP. Imagine a tiny electronic beetle. It has a rectangular body and 2 neat rows of 4 metal legs, or pins, on each side. These pins are its only connection to the outside world. They are how it gets power and how it talks to other components in a circuit. There's a little notch or dot at one end to help you know which pin is which, because getting them mixed up can lead to some very confusing and sometimes smoky results. Pin 1 is usually to the left of the notch, and you count counterclockwise from there. Each of these 8 pins has a specific job. Pins 2 and 3 are the all-important inputs, the inverting input, or minus, and the non-inverting input, or plus. These are the ears of the op-amp, listening for tiny differences in voltage. Pin 6 is the output, where the amplified signal comes out loud and clear. Pins 7 and 4 are for power, connecting to the positive and negative supply voltages that give the chip the energy it needs to work its magic. The other pins, 1, 5, and 8, are for things like offset nulling, which is a way to fine-tune the output, and 1 is simply not connected. It's a simple, standardized layout that has been used for decades. So, when you see a 741 on a circuit board, it looks like a simple, passive component. But don't be fooled by its quiet exterior. This humble black box is a bustling city of microscopic transistors, resistors, and capacitors, all working together in perfect harmony. It's designed to do one primary thing incredibly well. Take a tiny voltage difference between its 2 inputs and amplify it by a massive amount. How it achieves this feat is a beautiful story of engineering elegance. Now, let's get our virtual shrink ray ready, because we're about to go inside and see how this amazing little device really works. If we could carefully crack open that black plastic casing, we'd find a tiny square of shimmering silicon smaller than your pinky nail. This is the die, the heart of the 741. Connected to it are impossibly thin gold wires gracefully arching from the silicon die to the metal legs of the package, creating the electrical pathways to the outside world. It's on this tiny silicon canvas that the entire, intricate circuit of the 741 is etched. Using a powerful microscope, you would see a mesmerizing landscape of geometric patterns, the physical layout of dozens of transistors and other components, all built into the same piece of semiconductor material. To understand this complexity of silicon, engineers use a block diagram. Think of it as a high-level map that shows the main neighborhoods and how they connect, without getting lost in the details of every single street and building just yet. The 741's block diagram reveals 4 main stages, each with a crucial role to play in the signal's journey. First is the differential input stage, which acts as the sensitive front door. Then comes the intermediate gain stage, the power lifter that does the bulk of the amplification. After that, we have the frequency compensation stage, a sort of traffic controller that keeps the amplifier stable. Finally, the push-pull output stage acts as the strong delivery service, able to drive real-world loads. Each block in this diagram represents a collection of a few to several transistors and resistors working together as a team. The signal flows logically from one stage to the next. A tiny voltage difference enters the input stage. This stage processes it and passes a modified signal to the gain stage. The gain stage boosts it dramatically and hands it off to the output stage. The output stage then prepares the powerful signal for its journey into the rest of the circuit. It's a beautifully organized assembly line where each part knows its job and performs it with precision. This modular design is what makes the 741 so brilliant. By breaking down a very complex task, high gain, stable amplification, into smaller, more manageable subtasks, the original designer, Dave Fullagar, created a circuit that was robust, reliable, and easy to manufacture. It's a testament to the power of structured design. Before we zoom in on the individual transistors, keeping this block diagram in mind will be our trusty guide. It helps us see the forest for the trees and appreciate how all the tiny parts contribute to the op-amp's amazing capabilities. Now let's head to the first stop on our tour, the input stage. Our journey into the 741 begins at the front gate, the differential input stage. This is arguably the most clever and important part of the entire op-amp. Its job is to look at the two input signals on pin 2, the inverting, and pin 3, the non-inverting, and respond only to the difference between them. This is called differential amplification. If both inputs go up or down by the same amount, a common mode signal, this stage is designed to ignore it completely. This magical ability, called common mode rejection, is what makes op-amps so useful for pulling a tiny meaningful signal out of a noisy environment. Think of it like a pair of noise-canceling headphones for your circuit. At the heart of this stage is a special configuration of transistors called a differential pair, or long-tailed pair. It consists of two bipolar junction transistors, or BJTs, let's call them Q1 and Q2, whose emitters are connected together. The input signals are fed to the bases of these two transistors. The magic happens because they are forced to share a limited, constant amount of electrical current provided from below by a current source. This current acts like a fixed budget of water flowing through a pipe that splits into two paths. The voltage at the bases of Q1 and Q2 controls how this fixed current is steered or divided between the two transistors. Let's imagine what happens. If the voltage on the non-inverting input, the base of Q1, is slightly higher than the inverting input, the base of Q2, Q1 will turn on a little more, and Q2 will turn on a little less. This means more of the shared current will be steered to flow through Q1's path, and less will flow through Q2's. If the voltages are perfectly equal, the current splits exactly in half. If the inverting input's voltage is higher, the situation reverses and more current flows through Q2. The stage is incredibly sensitive. A difference of just a few millivolts is enough to steer almost all the current to one side. This steering of current is the first step in the amplification process. The output of the stage isn't a single voltage yet, but rather the changing currents flowing through the two transistors. These currents are then passed on to the next stage to be converted into a much larger voltage signal. Another key feature of this input stage is its very high input impedance. Because the inputs are connected to the bases of BJTs, they draw only a tiny, almost negligible amount of current from the signal source. This means the op-amp can listen to a voltage without disturbing the circuit it's measuring, like a detective watching from afar without interfering. So, our differential input stage has successfully converted a tiny voltage difference into a change in how current is split between two paths. But how do we turn this current change into a big voltage signal? And how did we get that stable, constant current for the differential pair in the first place? The answer to both questions lies in another wonderfully elegant circuit building block, the current mirror. A current mirror is exactly what it sounds like. It's a circuit, usually made of two transistors, that takes one current as a reference and provides a nearly identical copy of that current somewhere else. In the 741, a current mirror is used to provide the constant tail current for the differential pair we just discussed. This ensures that the total current shared between Q1 and Q2 is always the same. which is essential for good common mode rejection. But the more visible role for current mirrors is in the next part of the input stage, where they act as an active load. Instead of using simple resistors to convert the collector currents of Q1 and Q2 into voltages, which would be inefficient on a tiny silicon chip, the 741 uses a clever current mirror arrangement involving transistors Q3 and Q4. Here's how this active load works its magic. The current flowing out of the first input transistor, Q1, is mirrored by the active load. The current from the second input transistor, Q2, flows into this same point. Because one current is being mirrored and subtracted from the other, the circuit effectively performs a push-pull action. When the input voltage difference causes more current to flow through Q1 and less through Q2, the output of this stage changes significantly. This arrangement is brilliant because it not only converts the differential current into a single-ended voltage output, but also provides some voltage gain itself, all while using transistors that are much smaller and more efficient than large resistors on an integrated circuit. This technique is a cornerstone of modern analog IC design. Using transistors as active loads instead of passive resistors allows designers to achieve very high voltage gains in a small amount of silicon area. Resistors on an IC take up a lot of space, especially large-valued ones. Transistors are compact, and when used in clever configurations like current mirrors, they can behave like resistors with extremely high values, leading to massive gain. This is a key reason why a tiny chip like the 741 can boast a voltage gain of 200,000 or more. It's all about using the components you have in the smartest way possible. The signal, having been expertly received and prepared by the differential input stage, now arrives at the powerhouse of the op-amp, the intermediate gain stage. If the input stage was the sensitive ear, this stage is the mighty voice. Its one and only job is to take the relatively small voltage signal from the input stage and amplify it tremendously. This is where the majority of the 741's massive open-loop gain, that famous number of 200,000 volts per volt or 106 decibels, is generated. It's a simple stage in concept, but it's incredibly effective at its task. This stage is essentially a high-gain amplifier built around a single transistor, Q17, in the classic 741 schematic. It's configured as a Common-Emitter amplifier, a textbook arrangement known for providing significant voltage and current gain. The output from the active load of the input stage is fed into the base of this transistor. A tiny change in the base voltage causes a much larger change in the current flowing through Q17's collector. This large change in current flows through another active load, a circuit element that acts like a very large resistor, which in turn creates a very large change in output voltage. You might be wondering, why do we need so much gain? A gain of 200,000 seems excessive. If you put a 1 millivolt signal in, you'd expect 200 volts out, which is, well, impossible with a typical 15-volt power supply. This is where the concept of negative feedback comes into play, which we'll explore more later. For now, think of this huge, open-loop gain as raw potential. By having an almost infinite amount of gain to work with, we can use external feedback components, resistors, and capacitors to tame the op-amp and make it do precisely what we want, creating amplifiers with precise gains like 10 or 100, or filters with specific frequency responses. The high gain is the secret ingredient that makes the op-amp so versatile and predictable. The design of this stage is another example of efficiency in integrated circuits. It uses a Darlington pair configuration, transistors Q13A and Q13B in some diagrams, as part of its active load to create an extremely high effective resistance, maximizing the voltage gain without needing a physically huge resistor. The output of this stage, taken from the collector of Q17, will be a highly amplified, inverted version of the original differential input signal. It's now a powerful signal, but it's not quite ready for the outside world. It lacks the muscle to drive heavy loads, and it's so high gain that it's on the verge of instability. The next two stages will fix that. We now have a signal that has been amplified by a tremendous amount. However, with great gain comes great responsibility and a great potential for instability. At high frequencies, tiny unavoidable delays in the transistors can cause the phase of the signal to shift. If the phase shifts too much, by 180 degrees, the negative feedback we use to control the op-amp can suddenly turn into positive feedback, causing the amplifier to oscillate wildly and become, well, pretty much useless. It would be like a microphone placed too close to a speaker, resulting in that ear-splitting squeal. To prevent this, we need a stability manager, the frequency compensation capacitor. In the MA741, this takes the form of a single tiny capacitor, famously labeled C1 on the schematic. It's a 30 picofarad capacitor, which is an incredibly small value, but it has a massive impact on the op-amp's behavior. This capacitor is strategically placed within the intermediate gain stage, connecting the output of the stage back to its input. This is a technique called Miller compensation. It cleverly uses the high gain of the stage to its advantage, making the small 30 picofarad capacitor behave like a much larger capacitor. This has the effect of rolling off the amplifier's gain at higher frequencies. Think of it as a frequency-dependent break. At low frequencies like DC, the capacitor acts like an open circuit and has no effect, allowing the op-amp to have its full massive gain. As the signal frequency increases, the capacitor starts to act more like a short circuit, reducing the gain of the intermediate stage. It's designed to start rolling off the gain well before the frequency gets high enough for those problematic phase shifts to occur. It forces the op-amp's gain to drop to unity, a gain of 1, at a frequency where it is still stable. This is what gives the 741 its characteristic frequency response, huge gain at DC, which then rolls off at a constant rate of -20 decibels per decade. This internal compensation is a defining feature of the 741 and a major reason for its popularity. It makes the op-amp unconditionally stable, meaning you can use it in almost any negative feedback configuration without worrying about it oscillating. The trade-off is performance. This heavy-handed compensation limits the op-amp's bandwidth, meaning it's not very good for high-frequency signals. Its gain bandwidth product is typically around 1 MHz. More modern op-amps offer much higher speeds, but many are not internally compensated, requiring the designer to add external compensation components. The 741's built-in stability made it incredibly easy to use, and a perfect choice for countless applications. The signal has been sensed, amplified, and stabilized. Now it's time for the grand finale, delivering that signal to the outside world. This is the job of the output stage. The preceding gain stage provides a huge voltage swing, but it has a high output impedance, meaning it's weak. It can't supply the current needed to drive a load like a speaker, a motor, or even just the next stage in a complex circuit, without its voltage collapsing. The output stage is a current amplifier, or buffer. It doesn't increase the voltage gain, but it gives the signal the muscle it needs to drive real-world loads. The 741 uses a Class AB push-pull output stage. It consists of a complementary pair of transistors, an NPN transistor, Q14, to push current out to the load from the positive power supply, and a PNP transistor Q20 to pull current in from the load to the negative power supply. When the output voltage needs to go positive, the NPN transistor turns on and sources current. When the output voltage needs to go negative, the PNP transistor takes over and sinks current. This push-pull action allows the op-amp to efficiently drive the output both high and low. A special biasing network involving transistors like Q18 and Q19 is used to keep both the push, Q14, and pull, Q20, transistors just slightly turned on, even when there's no signal. This is the Class AB part of the design. It's done to prevent something called crossover distortion. If the transistors were completely off, there would be a small dead zone as the signal crosses from positive to negative, where neither transistor is on. This would distort the shape of the signal. The biasing circuit ensures a smooth transition between the two transistors, resulting in a clean output waveform. Finally, the 741 also includes short-circuit protection. Transistors Q15 and Q22 are there to monitor the amount of current flowing out of the output stage. If the output is accidentally shorted to ground or one of the power supplies, the current could spike to a level that would destroy the output transistors. If these monitoring transistors sense that the current is getting dangerously high, they activate and steal drive current from the main output transistors, limiting the output current to a safe level, around 25 milliamps. This is an incredibly valuable feature that has saved countless 741s from an untimely demise on the benchtops of students and engineers. We've followed the signal's exciting journey through the main stages of the 741. But our tour isn't complete without paying tribute to the unsung heroes, the biasing network and the power supply rails. These are the crucial support systems, the city's infrastructure, that allow all the glamorous amplifying stages to do their jobs correctly. Without precise biasing, the entire circuit would fail. The biasing network is a collection of transistors and resistors whose sole purpose is to generate the stable reference currents and voltages that all the other stages depend on. The most important part of the biasing network is the circuit that creates the reference current for the various current mirrors we saw earlier. In the 741, this is done using a special circuit called a Widlar current source. It uses a clever trick with mismatched transistors to generate a very small, stable reference current. This master reference current is then mirrored and scaled to provide all the necessary operating currents for the differential pair's tail current, the active loads, and the gain stage. This centralized approach ensures that all the stages track each other properly, even if the temperature or power supply voltage changes. The power supply rails, connected to pins 7, positive V, and 4, negative V, are the ultimate source of all energy for the chip. The 741 is designed to work with a dual or split supply. For example, plus 15 volts and minus 15 volts relative to a common ground point. This allows the output voltage to swing both positive and negative, which is essential for amplifying AC signals like audio. All the currents we've been talking about, the bias currents, the signal currents, are ultimately drawn from these power supplies. The positive rail provides the source for currents that flow down through the circuit, and the negative rail provides the sink for currents to return. The relationship between the signal and the power rails defines the operational limits of the op-amp. The output voltage can never swing higher than the positive supply voltage or lower than the negative supply voltage. In fact, for the 741, the output can typically only get within a couple of volts of each rail. This is known as the output voltage swing limit. Understanding the role of the power supplies is critical. They don't just power the chip. They define the boundaries of the world in which the signal lives and breathes. They are the ultimate ceiling and floor for the amplified output. So, there you have it. A journey from a simple 8-pin package deep into the silicon heart of a MA741 op-amp. We've seen how an ingenious arrangement of differential pairs, current mirrors, active loads, and push-pull stages work in concert to create a powerful, versatile, and stable amplifier. The 741 is a masterclass in analog circuit design, where every one of its roughly 20 transistors has a deliberate and crucial role to play. From its noise-rejecting input to its muscular short-circuit-proof output, it's a complete system on a chip. In the world of 2026, where we have processors with billions of transistors, why do we still talk about a humble chip from 1968 with only a few dozen? Because the 741 represents a fundamental turning point. It wasn't the first op-amp, but it was the first to integrate all the necessary components, including the crucial compensation capacitor, onto a single, monolithic chip that was cheap, robust, and incredibly easy to use. It democratized analog design, putting the power of a high-performance amplifier into the hands of a generation of engineers, students, and hobbyists. The principles pioneered in the 741 are still the foundation of countless modern op-amps. While today's op-amps are vastly superior in almost every metric, they are faster, have lower noise, draw less power, and operate from single power supplies. They still use the same fundamental building blocks. The differential input stage, the use of current mirrors for biasing and active loads, and the concept of a multi-stage architecture are all direct descendants of the 741's design. Learning about the 741 isn't just a history lesson. It's learning the fundamental language of analog integrated circuits. So the next time you see a schematic with that familiar triangle symbol, remember the incredible city of silicon it represents. Remember the elegant dance of currents being steered by the differential pair, the perfect copies created by the current mirrors, the massive amplification from the gain stage, and the strong push and pull of the output stage. The MA741 is more than just a chip. It is a monument to engineering elegance, a foundational teaching tool, and a testament to the idea that a well-designed solution can be truly timeless. Its legacy is etched not just in silicon, but in every modern electronic device that relies on the magic of analog amplification.